Good morning. Today I will discuss CFT, crystal field theory. This is very important in inorganic chemistry. What is its important features? There are many features. And number one, the metal ions point positive charges. That is, metal ion is considered as a positive mass of charge. Point 2. Ligands are assumed to point negative charge or negative ends. All interactions are electrostatic in nature. The ligands approaches along well-defined direction in the metal complex of a given coordination number and geometry. The d orbital present in the degenerate set have directional characteristics. Different repulsion interaction with incoming negative ends of the ligands are for different 5d orbitals. The different d orbitals which responds more end and more repulsion is raised d orbital, energetically less repulsion is proportional to lower, so that the energy barrier center is maintained. This is splitting of d orbitals, and there are 5d orbitals, degenerate sets, 2 sets, that is T2j set and EG sets, higher orbital, that is EG sets, and lower energy set, that is T2j set, and barrier of center 10 dq, and for it is for octahedral complexes, and the y T2j set d xy, d yz, d zx, and EG set, that is dx square minus y square, d z squares orbital is different to sets according to their energy splitting. The splitting is so adjusted that the center of the gravity, barycenter of the 5 degenerate d orbitals in a 6 negative charge is maintained. To maintain the splitting of 5 d orbitals, splitting barycenters, that is T2g set will go down, say x, and EG sets will go up, that is say by y. If E the energy of the each electrons pairs of the splitting, it must be so that is 10E equal to 4 d plus x plus 6 E minus y, that is 2x is equal to 3y, and also we get x plus y is equal to delta, that is delta means 10 dq for octahedral complexes. Solving this problem, we get x equal to 2 by 5 delta and y equal to 3 by 5 delta. A very important question, what is crystal field stabilization energy? It is defined as the extra stabilization gain due to the preferential filling or distribution of the electrons in split set of d orbitals under the influence of the crystal field of a particular geometry in the comparisons to the random distribution of the same number of the electrons in degenerate set of n d orbitals in metal atoms in the absence of d or in the free metal atoms, that is called crystal field stabilization energy. Here we format a stable one-sided orbital weak field, that is delta less equal to p, that is p means pairing energy, high spin octahedral complexes. Strong field, that is delta greater than p, that is low spin octahedral complexes. If we consider orbital d1, d2, d3, d4, d10, that is 1 in case of d1, this electron configuration will be T2g1, Eg0 for weak field, and CFC will be 4 dq0, and same for strong field, and del 2 d2, that is T2g2 Eg0, and CFC is equal to 4 into 2, that is minus 8 dq, and same for strong field, and d3, that is electronic configuration is T2g3 Eg0, and CFC is equal to 4 into 3, or that is minus 12 dq0, and same for strong field. And you can consider d4, that is for weak field, electronic configuration will be T2g3 Eg1, and CFC will be minus 10 12 dq plus 6 dq 0, that is minus 6 dq 0. And in case of strong field, it is different electronic configuration, that is will be 4 electron will be in T2G set, that is T2G4 is 0, and CFC will be minus 16 dq 0. If you consider D5, the electronic configuration for weak field, T2G3 is 2, that is CFC minus 10 dq 0 plus 12 dq 0 is equal to 0 dq 0. And for strong field, the electronic configuration will be T2G5 is 0 and CFC will be minus 12 dq 0, that is very much for high spin than high spin. D6, electronic configuration T2G4 is 2, that is minus 16 dq plus 12 dq 0 is equal to minus 4 dq 0. And strong field T2G6 is 0 minus 24 dq 0. D7, T2G5 is 2, that is minus 20 dq 0 plus 12 dq 0 is equal to minus 8 dq 0. For strong field, T2G6 is 1 and CFC will be minus 24 dq 0 plus 6 dq 0, that is equal to minus 18 dq 0. For D8 system, for high spin, that is T2G6 is 2, CFC will be minus 24 dq 0 plus 12 dq 0 is equal to minus 12 dq 0. And for low spin, CFC will be minus 24 dq 0 plus 12 dq 0 is equal to minus 12 dq 0. C, for D9 system, the electronic configuration for high spin T2G6 is 3, CFC will be minus 24 dq 0 plus 18 dq 0 is equal to minus 6 dq 0. And for weak field, for strong field, that is low spin, electronic configuration will be T2G6 is 3, CFC will be minus 24 dq 0 plus 18 dq 0 is equal to minus 6 dq 0. D10 systems, electronic configuration for octahedral high spin octahedral complexes T2G6 is 4, CFC will be minus 24 dq plus 24 dq is equal to 0 dq 0. And same for low spin complexes. The spin crossover region, it is very important question in CFT chapter and defined as, in some cases, high spin state may be energetically somewhat less than the low spin state, may be energetically more stable than this high spin state. In such cases, obviously, the energy difference between two spin states, octahedral complex is small and comparably to kT, that is thermal energy. According to Boltzmann distribution law, N is equal to N0 e to the power minus kT, and in these cases, the population of these two spin states will be governed by thermal energy, that is temperature. The temperature depends equilibrium between two spin states, that is high spin state and low spin state. That is called spin crossover region, where 10 dq is equal to P, that is P means pairing energy, and dq means crystal field stabilization energy. Till now, I see it, the electronic configuration of octahedral complexes. If we see tetrahedral complexes, then we can get these types of configurations. Here, d orbital, 5d orbital split, and Eg, that is E set. G means octahedral, and here tetrahedral complex. If we consider tetrahedral complex, there is no G, and that is E and T2, and there E, that is set will be dx square minus y square and dz square, and T2, that is dxy, dyz, dzx, and this is different and whole opposite of octahedral complexes. And it is mean that, it is remember that in case of tetrahedral complexes, only weak field ligands and form tetrahedral complexes, that is high spin complexes. No strong field complexes ligands or strong ligands form tetrahedral complexes. Only weak ligands, that is high spin complexes, means tetrahedral complexes. And here, the splitting these types and this barycenter is 10 dq, not dq 0, and this is only 10 dq. And what is relation between tetrahedral and octahedral complexes? Let's see. Delta T equal to 4 by 9 del 0. That delta T is means this crystal field energy of tetrahedral complexes, and del 0 means crystal field stabilization energy or crystal field energy of octahedral complexes. And delta T is always less than P, and hence low spin field and tetrahedral complexes are not possible. Thank you.